Hello everyone, welcome to TV Math. This is your study pattern for competitive exams. If you are new to this channel, please kindly consider subscribing. Subscribing is completely free of charge. It does not involve any costs. However, you will always get ahead and get notified whenever a new video is uploaded. So kindly do subscribe, like and share this video to all your friends. In our today's session, I will be taking you through part 2 for objective questions of a real analysis. So for those that are preparing for their final examinations, this will help you in revising and in your preparations for your final examinations. So we want to start with objective question number 31. In our previous session, that was in part 1, we looked at 30 objective questions. So in our today's session, we shall look at more than 40 objective questions, and this would be enough to take you through your final examinations. So basically, let us look at question 31, and as usual, you will have 30 seconds. You will have 30 seconds to find the answer. Then thereafter, we shall have to look at the answer together. And at the end of this video, please consider putting your total marks out of the total objectives that we shall have discussed. So keep putting those answers down, keep marking yourself, and challenge yourself to see if you are able to get those answers right. Okay, let us get into our today's session. So here is our question, and as usual, you have only 30 seconds. So the question says, which of the following sets is finite? And we shall look at our options. However, before we look at these options, you must know what finite sets are. So when we look at the options, we are given A, the set of prime numbers less than 100. So when we look at the set of prime numbers less than 100, we can easily count. We can easily state and list these elements within this given set. You can list it starting with 2, going with 3, going with 5, and so on, up to 97. So these are the prime numbers. So it means we can count the number of elements in this given set. So it means this one here, the numbers can be counted. So this has got limited number or limited count. So we can easily get to the number there. Then when you look at the set of natural numbers, this is actually countably infinite. This is countably infinite. This is countably infinite. So it is countable but infinite. The set of real numbers, this is also uncountably infinite set. Then the set of rational numbers, this is countably infinite set. So this is countably infinite set. So basically, the set that will be finite will be the set of prime numbers less than 100, and that will be part A as the answer. So we look at the next question. So we look at this, which of the following is true about a bijection? So for the different questions we have looked at, it should be easy now to look at what a bijection is. So a bijection is simply that which shows a one-to-one correspondence between two sets. So for the different questions we have seen, this should be easy to note out. So that is about a bijection. Okay, so after that, we shall look at the next question. What does it mean for a set to be uncountable? We talked about countable sets. So for uncountable sets, it should be also easy to note. So that is, it cannot be placed in a one-to-one correspondence with the set of natural numbers. That is uncountable. So for the set to be uncountable, it cannot be placed in a one-to-one correspondence with the set of natural numbers. If it can be placed in a one-to-one correspondence with the set of natural numbers, then we shall say it is countable. So from the definition, you should be able to give the answer for A. From the different questions that we have already discussed for countability of sets, this should be easy for you. So that would be part A as the answer. We look at the next question. The set of real numbers between 0 and 1 is, so if you recall about the concept for a Cantor set, this should be easy. So basically, the set of real numbers that is between 0 and 1, if you recall from the Cantor set, this set here is uncountable. This set is uncountable. So this can be proved using the Cantor's diagonal argument, if you recall about a Cantor's set. So when you look at the option A, they are saying is a finite, but we know that for a finite set, they have a fixed number of elements. And when you look at such a set here, which is consisting of elements between 0 and 1, this set here has got actually uncountably many elements. This set has uncountably many real numbers. So for that case, it cannot be finite. Then countability. We recall that countable sets are finite, or in bijection with the set of natural numbers. A countable set is that set which is finite, or in bijection with the set of natural numbers. However, when you look at such a set, this one will not be actually countable, because when you consider the rationals in this given set here, or the real numbers in this given set, they cannot be counted. So that is uncountable. So we cannot have this option true. And then when you look at this, this is not true, because we are talking about the set 0, 1, which set here has got elements. For example, 0.5 is in this set, so it cannot be empty. So this one will also be out. So the set of real numbers between 0 and 1 is uncountable. You can refer this basically by looking at the Cantor's diagonal argument, which explains this better, why this one is actually uncountable. So that would be C as the answer. What is the difference between a sequence and a set? So basically, to distinguish between the two, we need to recall some of the definitions for a sequence and for a set. So a sequence is basically a function. So that is a given function that has elements from the domain, that takes elements from the domain, which domain is the set of natural numbers, and then to the codomain, which codomain can be any given set here. So to that. So this is a sequence. So that function that takes elements from the domain, which is the set of natural numbers, to any given set. So when it means if we pick n from this given set, for example, here we get an in the codomain. So it means that here the order is inherent. When you talk about the sequence, which is 1 2 1. This one here differs from when you have a sequence 1 1 2. So the order is very important when you are talking about what we call a sequence. However, when you are talking about a set, when you are talking about the set, the membership is the only property when you are talking about the set. For example, when you are having a set 1 2 and you are having this set here and such a set 1 1 2. So these two sets here, instead of writing it like this, you can write it like this. What is important is the what? Is the membership value. So this is 1 2. So having 1 1 2 and having 1 and 2, actually here you even don't need to repeat that. So this set and this one will be the same, which is not the case. Which is not the case for sequences. So for a sequence, order is very important. For a set, what is important is basically about the membership. So the ordering is the fundamental difference, as it allows sequences to model progression or indexing, unlike sets. So that is the most important thing that distinguishes the two. So looking at the given options, a sequence is ordered while a set is not. So this is very true. This is very true. So a sequence is finite, a set is infinite. So basically, sequence has no repetitions, while sets do. This is not true because sequences permit repetitions, which is not the case for the sets. So this is not true. A sequence is always countable. This is not true. There are some which are not countable. So this will also not be true. So the answer will be part A. So the fundamental difference here is about what we call ordering. So ordering is what distinguishes sequences with sets. So what is a monotonic sequence? A monotonic sequence is that sequence that is either entirely non-increasing or non-decreasing. So that is by definition, and for that case it means this will be true. A sequence that alternates sign, this one here actually violates monotonicity. So this violates monotonicity, so this is out. A constant sequence, these are monotonic but are trivially so. So the definition is broader, so this one will not be the best option. Sequences with terms approaching zero. Sequences with terms approaching zero may be monotonic, but may also not be monotonic. So for that case, it means this will also be out. So the correct answer is that a sequence that is either entirely non-increasing or non-decreasing, and that would be the answer. What is the limit of the sequence an? What is the limit of the sequence an equaling to 1 over n as n tends to infinity? So as n tends to infinity, what happens to this? So basically, you need to look at the sequence. This sequence here is defined. N is picked from the set of natural numbers. So if we begin with n equaling to 1, it means this will be 1. Next will be a half, a third, 1 over 4. And this keeps on increasing. If it reaches 100, this becomes 1 over 100. So this keeps on increasing. So as you look at this, you realize the values keep on decreasing, keep on decreasing. So the values keep on decreasing, and as they decrease, they are coming towards some specific value. So when you look at this one here, these ones, as it keeps on decreasing, it is tending to a value which is 0, because it is becoming smaller and smaller. So as n keeps on increasing, this sequence here will be tending to 0. So for that case, it means the limit for such a sequence is what? Is 0. So the answer will be A, which is a 0. If n is equal to that, what type of sequence is this? Oh, we have the answer there already. So this sequence here is actually oscillating. The reason is, when you look at such a sequence, this will be start with 1. We are talking about n picked from the set of natural numbers. So start from n equaling to 1, to 2, to 3, and get the sequence. So if n is equal to 1, this will be -1, n to 2, +1, -1, +1, -1, +1, and this goes on forever. So when you look at this sequence here, you realize it is alternating indefinitely between -1 and +1. It is alternating indefinitely between -1 and +1. So this shows a periodic oscillation without settling to a given value. So for that case, it means this sequence is oscillating. So that one will be an oscillating sequence. So this is almost same as the one that we have actually seen. So this you should also be able to give the answer right away. We talked about such a sequence, so it is a similar question to the one we have just looked at. So this the limit of this sequence is 0. So the sequence is decreasing, but it cannot exceed 0. So this should be easier for us now. So which of the following sequences diverge? Okay, so this one we have seen this converges and goes to 0. This we have seen this keeps on alternating between -1, 1, -1. So this is an oscillating sequence. So this one here oscillates or alternates between -1 and 1. So the limit does not exist here. The limit does not exist, though it remains bounded. Then when you look at this one here, so this is convergent. So this one converges and it goes to 0. So this one here diverges by oscillation. This diverges by oscillation by deviating between -1 and 1, though it remains bounded. Then when you look at C, the C here, so this has got terms like 1, 2, 3, 4, and so on. This has got these terms here, as we put n equaling to 1, to 2, to 3. So when you look at this one here does not come to a specific value. So this one is diverging. And then when you look at this one here, the terms of this sequence are 1/1, 1 squared remains 1, 1 over 2 squared, that is 4, 1 over 9, and so on. So you realize the terms keep on decreasing, and as n tends to infinity, it means that these terms here will be coming closer to 0 as well. Though this one and this one all converge to 0, these two converge to 0. Though this one here converges or reaches the limit faster compared to this, because this consists of 1, 1 over 2, 1 over 3, 1 over 4. But as this one is 1, this is 1, this is 1 over 4, 1 over 9. So these are decreasing faster compared to this. So this and this converge or reach their limit is 0. Then this one here diverges, but it diverges by oscillation. So this will be diverging, and it will be going to positive infinity. So our answer is C. So our answer will be C. So that will be the answer. C will be our correct option. So what is a Cantor set? What is a Cantor set? A set of all irrational numbers. This is basically not true. A Cantor set is that set that has got the real numbers between 0 and 1. So that set is a set of all irrational numbers. This is not true, because we can get irrational numbers which are outside this. A subset of real numbers obtained by iteratively removing the middle thirds of intervals. This is very true. The set of all rational numbers, this is not true. The set of integers, this is not true. So our answer will be B. Okay, so we look at that. What is the length of the Cantor set? So what is the length of a Cantor set? Okay, so we need to look at the length of a Cantor set. So basically, to look at the length of a Cantor set, you recall that when you are constructing a Cantor set at a given stage, that is at stage n. At stage n, you have 2 to power n minus 1 in open intervals. These are open intervals of length 3 to power n to power negative n, because it is 1 upon 3 to power n. Of length 3 to power negative n, which are removed. So you have 2 to power n minus 1 open intervals of these lengths removed. Okay, so the removed lengths at n, the removed lengths, so the removed length at stage n, the removed lengths at stage n will be 2 to power n minus 1 divided by 3 to power n, divided by 3 to power n. So the total removed length will be, the summation of n equaling to 1 up to infinity of 2 to power n minus 1 divided by 3 to power n. And of course, this is same as having 1 upon 3 divided by 1 minus 2 out of 3, which is same as 1. So because this will be a geometric series. So basically, starting from the initial interval of length, which will be 1, starting from the initial interval of length, which will be 1, it means the remaining measure will be same as 1 minus this value 1, and this gives us 0. So basically, the length of the Cantor set is 0. The length of a Cantor set is 0, because when A is 1, 1 is simply the length of the initial interval. The length of the initial interval, as you are constructing, you must be remembering this. So the length of the initial interval is 1. So this is the length of the initial interval before you remove anything. Then a third, this is the length removed at the first stage. If you recall, the length removed at the first stage from here to here will be removed. So that is the third, because this is a third, this is 2/3. Then infinite, this is impossible because C, the counter set, is of course a subset, is a subset or is equivalent to this, so it cannot be infinite. So basically the length of the counter set is 0. The length of the counter set is 0. So you must know the process of constructing the counter set and how we arrive at this 0, how we get the open intervals, how we get the length of the removed parts, and how we come up with these lengths here. So basically that is a small procedure that we follow when we are looking at the lengths of the counter set. So you need to go back and try to check how we construct a counter set. So the next question says the counter set is, so we looked at the counter set as the set of real numbers, a subset of real numbers in this given interval. So it cannot be countable, not finite, is not empty, so it must be uncountable. So this set here is uncountable, and that is the answer. So which property of the counter set is true? So let us look at the given options. So we are told that A, it is dense in a 0, 1. This is false because it is the counter set C is nowhere dense. Is nowhere dense. Is nowhere dense in this interval. Is nowhere dense in this interval. So in other words, it is not dense in this interval. The complement is dense because we have open intervals removed. The open intervals removed are dense. So its complement is dense, but for it is nowhere dense. B, it is closed and has no interior points. It is closed and has no interior points. This is true because the counter set is closed. This set here is closed. This set is closed in R. This set is closed in R and has an empty interior. And has an empty interior because when you recall in the construction of a counter set, no non-empty open intervals is contained in the counter set. This is due to the iterative removal of dense open sets, so making it totally disconnected. So that is why we say it is closed and has no interior points. So this is true. Then open set, it is an open set. When you look at that, our set is closed, not open set. Then it contains all real numbers. This is not true because we have real numbers other than these ones that are enclosed between 0 and 1. So our answer is B. The Cantor set is an example of which set? Finite set. This is not true. This set here is actually not finite. So this is uncountable. So this is out. Bounded open set. Our set is bounded closed set. This is a closed set. So if it is open, it means it would have been like this. It does not contain its interior points. However, this contains its interior points. So it is not bounded open set. Then perfect says closed and contains all its limit points. This is very true. And bounded set, this is not true because our set is bounded between 0 and 1. So our answer here will be C. Okay, what is the absolute value of a real number? So absolute value of real number, you must know how to define the absolute value of a number. So the absolute value of x is same as x if x is greater than 0 and negative x if x is less than 0. Okay, so what is the absolute value of a real number? So the absolute value of a real number, so the square of x, okay, so when we look at the square of x, x squared is always, x squared is always non-negative, is always non-negative, okay? So not necessarily, it does not necessarily talk about the magnitude of x. Then B, the distance of x from 0 on the real number line. This is very true. The distance of x from the real number line is what we can term as the absolute value of a real number. This is very true. Then C, this is incomplete piecewise definition because when you look at this one here, negative x if x is less than 0, for by definition this must also include, that is magnitude of x is x for x greater or equal to 0, negative x for x less than 0. So this is incomplete because this one here should be negative x if x is less than 0 or x if x is greater or equal to 0. So this one is incomplete. This is incomplete. Then none of the above, this one will be out. So the distance of x from 0 on the real number line will be our answer. This is incomplete because of this greater or equal sign. So basically that is about that question. Let us look at the next question. So we are looking at magnitude of negative 7. So magnitude of negative 7 should be equal to 7. Magnitude of a positive, magnitude of a negative is positive. So magnitude of positive 7 is 7. Magnitude of negative 7 is 7. So we are taking the numerical value of what you are looking at. So magnitude of negative 7 is 7. So which of this is true for absolute values? Magnitude of x plus y is equal to this. This is not true. This should be less or equal to. So this is out. This one here is true. Magnitude of x times y is same as magnitude of x times magnitude of y. This is true. This one here is not true. Magnitude of this should be greater or equal to the magnitude of the whole of this. So magnitude must be there. Magnitude of x is equal to x for all x. This is not true. Magnitude of x is not equal to x for all x. So our answer will be B, where we have magnitude of x dot y is same as magnitude of x times magnitude of y. So that will be the answer. Which inequality represents the triangle inequality for absolute values? So this one at this given time should be true. When you look at this one here, B would be true if this was there. Then C, magnitude of x, this is not true. This is not true. Then none of the above. This is of course incorrect. So basically, when you record the triangle inequality, it states that for all real numbers x and y, then magnitude of x plus y should be equal to this. Then this one here would be true if this was also a minus, not a positive. And this one here is there. So this one is completely out as well. So this one here is also completely out. So we have this as the best option. So we are looking at what is the magnitude of x minus y geometrically. So geometrically, it is basically the distance between x and y on the number line. So we have already defined what magnitude of x is. So that is the distance from, if you are looking at magnitude of x, that is like x minus 0. So that is the distance between x and 0, or the distance from 0 to x on the number line. So when you are looking at x minus y, the distance between x and y on the number line. So that is how we define the magnitude of any given number geometrically. So that is with respect to the real number line. So that is the distance between x and y on the real number line. And that will be the answer. So next we are looking, a set of real numbers is bounded if the set of real numbers is bounded if 1, if it is finite. This is not true. So finite sets are bounded sets, but we also have infinite sets which are uncountably infinite, which are also bounded. So it has both an upper and lower bound. This is true. It is countable. We have countable sets which are not bounded. So this is not necessarily true. Closed sets, if it is closed, does it mean it is bounded? Closed sets like R are unbounded. Then we have open bounded sets. like a 0, a 1, which exist also. So basically, this is also not true. So a set of real numbers is bounded if it has both an upper bound and a lower bound. What is an upper bound of a set S in R? So you need to recall the definition of an upper bound. Okay, so to look at the upper bound, if you are having a given set S from the set of real numbers, then if there is a real number, for example M, if there is a real number, for example M, such that the element S, which is less or equal to this M here, for every S that we are picking from this set S here, then this can be any number at or above the supremum S. So if you are having elements of S and you are having a number M such that all the elements of S are less or equal to that number M, this M here will be said to be an upper bound if it can be part of this set here, or it might not necessarily be part of the set S. It might not be part of the set S as well. So it can be in the set or outside the set, because when you consider a set S, for example 0, 1, when we are to talk about the upper bound, this one can be an upper bound, but an element like 2, an element like 3, like 4 will also be an upper bound of this set. So 1, when you look at that, M will qualify to be an upper bound if M is greater or equal to the elements within this given set. So for that case, an upper bound of a set S is a number that is greater than or equal to every element in that set. This is very true. The maximum of S, not necessarily, because the maximum of S must be part of the set, but this M may or may not be part of the set. A number less than all elements, this is not true. A limit point of S, this is not necessarily true, because when a limit point, you have a limit point of this set here, it means that every neighborhood of that limit point will contain infinitely many points of S. So it means this might not necessarily be an upper bound. So an upper bound should be that element that is greater than or equal to elements in S. As we have seen, 1 can be an upper bound, but 2 can also be, 3 can also be. So that will be an upper bound. So which of the following is true for a bounded set of real numbers? For a bounded set of real numbers, 1, we are having it must be finite. So when you look at this, so finite sets are bounded, but in finite sets like 0, 1, when you look at this 0, 1, this is also uncountably infinite. So basically finite sets are bounded, but infinite sets like this one here, which are uncountably infinite, or even when you consider the sequence 1 over n, for which n is picked from the set of natural numbers, this is also countably infinite and are also bounded. So this might not be the criteria for a bounded set. Then it is contained within some interval. This is very true. This is very true. This is very true, because when you look at a set, if you consider a set S, which is a subset of R, this is bounded if there exist real numbers M and M, for which this M here is less or equal to M, such that this M is less or equal to the elements of S, which is less or equal to M, for all S which is picked from the set of for all S which are elements of this capital S. So you realize that the elements of S are actually within a given interval, which is M and capital M, which is M and capital M. So a closed bounded interval will always work. So when we say it is contained within some interval, this will be true. It contains its supremum. Okay, so a bounded set have a supremum. Then, however, the supremum might or might not be part of that given set. So this might not necessarily be true. Then it is uncountable. This might not necessarily be true. So basically, it is contained within a given interval, and that will be the answer. What is the supremum of a set S? Supremum of the set S. We are looking at the supremum of the set S. So the supremum of the set S, A, the greatest element in S. So part A, the greatest element in S, that is what we call the maximum of S. And this exists only if the supremum is part of the set. You recall, if you are having the supremum, which is part of the set, then the greatest element exists and it will be actually the supremum. However, this is not the supremum of a set. Okay? Because the supremum might not necessarily be part of the set. But when you say the greatest element in S, it is not necessarily that the greatest element will be the supremum of that set. Then the least upper bound of S, this is true, the least will be greater than U minus epsilon. So for any epsilon greater than 0, there should exist S. There should exist S picked from the set such that S is greater than U minus epsilon, meaning that no smaller number satisfies this given condition, meaning that U must be the least value in that given what? In that given set of upper bounds. So that is the least upper bound. Then the smallest element, this is out, and that would be the answer. What does it mean if a set has no upper bound? If a set has no upper bound, it means it is unbounded. This is out, and this is also out. So it is unbounded. If the set has no upper bound, so it means it will not be bounded. So what does it mean for a sequence AN to be bounded? For a sequence to be bounded, let us look at the options. AN converges to 0. Converges to 0 implies a boundedness. However, you need to recall that bounded sequences need not to converge to 0. It is not necessarily true, so this will be out. There exists real numbers M and this such that M is less. This is very true. If this exists, it means M is bounded between this AN, the sequence is bounded between this and that. So it means here it will be bounded. AN is finite, not necessarily that it has to be finite. Is monotonic, not necessarily, because for monotonicity it means it is non-decreasing or non-increasing. But such sequences can be unbounded as well. So this might not necessarily be true. So the answer is this. It must have the lower bound and the upper bound. So which of the following sequences is bounded? Which of the following sequences is bounded? So we look at the answer. So when you look at this sequence, this is like 1, 2, 3, 4 when you put n. So this sequence here is unbounded above, because you realize the supremum, this one is tending to infinity. So it is tending to positive infinity. So the supremum of this sequence here is actually positive infinity. So it continues. So this is 1, this is 4, this is 9, this is 16, and so on. So still this one here grows faster. So this is unbounded above. This is unbounded above. So here it is also unbounded above, because it keeps on growing bigger and bigger. So this is unbounded above as well. So this is also unbounded above. Okay, so when you look at this sequence here is between 1. So okay, let us first list the elements. 1/3. So it goes on, but it does not exceed 0. So even if n keeps on increasing, it does not, the sequence does not exceed 0. So you realize this sequence is between 1 and 0. So 0 less than n less than or equal to 1. So it is between 0 and 1. So it cannot go beyond this. So when you look at this one here, let us get the elements of this. So this is -1 to power 1 times 1, and -1 to power 1 times 2, -1 to power 2 times 3, so and so on. Okay, so this will give us a -1. This is to power 2, -1, then 2, -3, then 4, and so on. So this keeps oscillating with increasing magnitude. So it is unbounded above and below. So this will also be unbounded above and below. Okay, so basically this is unbounded above, this is unbounded above, this is bounded above and below, this is unbounded above and unbounded below. So looking at the sequence which is bounded, it will be C. A sequence is bounded above if a sequence is bounded above if all terms of the sequence are less or equal to some fixed number. This is very true. The sequence is finite, not necessarily. The sequence not necessarily true. So all terms of the sequence are less or equal to some fixed number. So for that case, you will be able to say your sequence is bounded above. Okay, so let us look at the next question. So if an is equal to this, is the sequence bounded? Yes or no? So this sequence here is bounded. When you look at such a sequence, it alternates between -1, 1, -1, 1. So it does not go beyond -1, neither does it go beyond +1. So it alternates between -1 and 1, and for that case, it means our sequence is between -1. This sequence here is between -1 and +1. So it is bounded between these two values, -1 and 1. So this sequence will be bounded. So what is the least upper bound of a set? The least upper bound of a set, we have definitely talked about this when we were talking about the supremum, and we said the least upper bound, or what we call the supremum of a set that is bounded above, is the smallest real number u, such that is the smallest real number u such that s is less or equal to u. So where s, these are elements from this given set. Yeah. So for all the elements of this given set, be less or equal to u if u is our least upper bound for the supremum. If it is the supremum, then all other elements must be less or equal to that u. And again, so this is for the case that u is an upper bound, meaning that u must be an upper bound first for it to qualify to be the least upper bound. So if u is the upper bound, if it qualifies to be an upper bound, then the one that now makes it the least upper bound, it should be that no smaller number has got the property, that for every epsilon greater than 0, there exists an element from that set such that that element will be greater than u minus epsilon. So if the two are satisfied for u, then u will be called the least upper bound. Okay, so when you look at the options, the greatest element in S, this is not necessarily true, as we saw. Be the smallest number that is greater than or equal to every element of S. That is true. This U must be an upper bound, and it must be the smallest among the upper bounds. So this should be true. The smallest element in S, this is not necessarily the average. This is not true. So it should be the smallest number that is greater than or equal to every element of S. So which of the following is not true about the supremum of the set? Which is not true? It may not be an element of S. This is true. The supremum of the set need not to be in S. So this is true. It is always the maximum. This is not necessarily true. The maximum of the set must be an element, the greatest element of that set. However, the supremum may or may not be part of the set. C, it is an upper bound. This is true. For an element qualified to be the supremum, it must be an upper bound first of that given set. Then D, it is unique if it exists. This is very true. The least upper bound, if it exists by completeness of R, is unique, meaning no two distinct upper bounds can both be least. So this is also true. So which of the following is not true about the supremum? Answer will be B. Answer will be B. It is always the maximum. It is not necessarily that it must be the maximum of that given set. A set S has a supremum if, this should be easier for you to notice. S is finite, not necessarily countable, not necessarily. S is bounded above. If it is bounded above, then S has got a supremum containing all its limit points. This is not necessarily true. So the answer should be part C. So like the previous question, this should also be easier for you to notice. The infimum of a set S R, S which is an element of R, exists if A is infinite, not necessarily. S is closed. Closed sets can be unbounded below as well, because when you look at a closed set like negative infinity, when you look at such a set, negative infinity and 0, negative infinity and 0 is closed with infimum, which is a negative infinity, and of course the supremum is that. Okay, then when you look at also open sets, when you consider an open set like this, this set has also got the infimum of what? Of 0. So it is not necessarily that the set must be what? Must be closed. Then S is bounded below. This is very true, as we have seen in the previous case. S is countable, not necessarily true. So because we can have countable sets that are unbounded. So basically that is all about that question. So we look at the next question. So if S is equal to that, what is the supremum of S and infimum of S? This is a closed set. So we shall have the infimum as 0 and the supremum as 2. So infimum 0, supremum 2, that is part B. This is not true. This is not true, because if this negative 1 is even not part of this set, this is supremum 1, infimum that. This is not true. This is incorrect. This is not true, because 1 is even an interior value. 1 is an interior value, so it cannot be the supremum. So our correct answer will be part B. We have so far talked about the supremum and infimum. So let us answer this one very fast. What is true about the supremum and infimum of a set? Both must belong to the set. That is not necessarily true. Either may or may not belong to the set. This is true. Infimum and supremum can be or cannot be part of the set. So it is not necessarily true that they must be part of that set. They can or cannot be part of the set. Both must be limits of the set, not necessarily. The supremum is always finite, not necessarily. And part B will be our answer. So next, if S is equal to 0, 1, what is infimum of S? So the infimum of S, this will be 0. So that would be 0. So the infimum of S is 0. However, 0 is not part of the set. So this would be correct, but it omits the important word that 0 is not part of this set. Though 0 is the infimum, but 0 is not part of this set. So this one since we have the one that describes it well, 0, but 0 is not in S, this one will be the correct option. Then and find this is not true. Negative 1, when you look at negative 1 is a lower bound, but not the greatest lower bound. So negative 1 cannot be the infimum, though it is at the lower bound. So we have 0 as the infimum, but it is not in S, and that would be the answer. Okay, so we are having, if an is equal to that, we have seen this is the sequence of this nature, and so on. What is the supremum of this sequence? So when you look at this sequence, we can easily see that this sequence lies between -1 and +1. So meaning that this -1 is the infimum, and this one is the supremum of that given sequence. So for that case, a -1, this is actually the infimum, so this we are talking about supremum. This is the supremum, +1. 0, 0 is neither an upper or lower bound, so it means this one has no impact, nothing to do with the supremum of this. Is undefined, this is out. So that is what we shall get. The supremum will be 1. If they ask about the infimum, it will be -1. So that would be the correct option B, which is equal to 1. So we have so far talked about this sequence so many times as 1, 1/2, 1/3, 1/4, and so on. And this one here is coming towards a 0. And we have seen this sequence is between 0 and 1. So 0 is not part of this. However, the terms are tending to 0. Though 0 is not part of this, is not one of the terms of this sequence. But all of them are approaching a what? A 0. But 1 is part of this. So 0 is the infimum, though it is not part of the sequence, is not part of the terms. Then 1 is the supremum. 1 is the supremum, and 1 is, of course, within the terms. So 1 is part of the terms. So that's why we are having less or equal here. And this one here, we are not putting it because 0 is not part of the terms. So this is the supremum, this is the infimum. So the infimum of this sequence is 0. And find this is not true. Infinity, this is not true. This applies to sequences, for example, the unbounded below sequences or unbounded above sequences. Okay, then and find this is not true. 1 is actually the supremum. It can also be the maximum of this set here, of this, and 0 can be the infimum, but 0 cannot be the minimum. So this one has got no minimum, because to be a minimum, it must be part of the set. To be the supremum, it must be part of the set. Like 1 is the supremum, though 1 is also a maximum, because 1 is part of the set. But 0 is the infimum, though 0 is not a minimum, because 0 is not part of this set here. So that is about the infimum, and basically we have also looked briefly about the maximum and minimum of that set. So whenever a question asks about minimum, maximum, you should be able to distinguish them very well. Okay, so we look at the next question. So we have the next question there, and please don't forget to subscribe to this channel. If you find this video helpful, make sure you like, share, and subscribe. Be part of this great family. So we are looking at what is the maximum of a set. Maximum of a set. So we have, in our previous example, talked about maximum, minimum, supremum, and infimum. So what is the maximum of a set S? So we are talking about the maximum is the least upper bound of S, then the greatest element in S if it exists, then we have the smallest element in S, and an element that is greater than all other elements in S but not necessarily in S. Okay, so let us look at the answer for this. So the maximum of a given set is the greatest element in that set. Is the greatest element in that set. So the greatest element in S if it exists. So that will be P. The least upper bound, that is about the supremum, but as we can see, it is not necessarily that the least upper bound will be the greatest element in that given set. Okay, so the maximum of a set S is the greatest element in S if it exists. A set S, which is an element of R, has a minimum if we have these different options. We shall talk about them. If it is bounded below. So if it is bounded below guarantee infimum. If it is bounded below, then it means it has got the infimum. So, but if it has the infimum, it does not mean it has the minimum. Because if, for example, you have this set 0, 1, this set here has the infimum, which is 0. But the minimum does not exist. The minimum is actually also not 0. So the minimum does not exist. So it has no minimum. No minimum. So it has no minimum because when you look at minimum must be the smallest element in this set. So 0 is actually not the smallest element in this set because 0 is not part of this set. So the infimum is 0, but it has no minimum. So if it is bounded below, it does not mean it has got a minimum. Then infimum is an element of S. If the infimum is an element of S, for example, if it was like this, so the infimum is 0, and 0 is part of this set. So for that case, if the infimum of that set belongs to the set, then it means the infimum is actually the minimum, and this will be true. Okay, so the minimum S exists if the greatest lower bound, or if the inf of S is an element of S, then it means the infimum will become the minimum so long as the infimum is part of that set. It is finite, so it is finite, not necessarily that if it is finite, it will have the what? It will have the minimum, because we have got an infinite non-empty sets which have got minimum. So it is closed. It is closed. We have closed sets which may lack the minimum if unbounded below. For example, negative infinity and 0 has the minimum is not there, so it has no minimum. So it has no minimum, but it is closed. So basically, this does not necessarily mean we shall have a minimum. So the correct option here will be part B. So for S equaling to that, what is maximum of S? So the greatest element in S, the greatest element in S, 0. When you look at 0, 0 is not in S. and 0 is smaller than all elements, and yet we need the maximum or the greatest value. So this is out. 3, when you look at this, you realize 3, what is the maximum? So when you look at 3, so let us look at 3. So this 3 is the maximum. That is right. This is right because this is the maximum, the greatest element in that set. Supremum of S is equal to 3, but maximum does not exist. Supremum is 3, but maximum does not exist. This is not true because 3 is an element of the set. So the maximum is an element of the set, and if the maximum is an element of the set, then it means the maximum exists, and that maximum is same as the supremum. So this one is not true when you say the maximum does not exist. D is undefined since S is finite. This is completely out. So the answer will be B. So B will be the correct option. So the largest element is 3, and 3 is an element of this set. So this should be easy to notice. Which set has no maximum? This set has got a maximum. 0 is the minimum, and it happens to be the infimum. This is the supremum, and it also happens to be the maximum. So it has got the maximum, minimum, supremum, and infimum. This set here, negative 1, 1, 0, 1. This one here, okay, there is a mistake here. This should be negative 1, 0, 1. Okay, so this set here has the minimum, which is equal to the infimum, and all of them are equal to negative 1. Supremum, which is equal to the maximum, because supremum is part of the set, which is also 1. So this is negative 1. So this set here has the infimum of 0, supremum of 1. Then it has no minimum because 0 is not part of the set, no maximum, 1 is not part of the set. So this one here is an open bracket, meaning 0 and 1 are not part of this set. Okay, so which set has no maximum? It will be C. If maximum of S exists for S, which is a subset of R, then if the maximum of S exists, then what does it imply? S is unbounded above. If the maximum is there, remember maximum is the greatest element in that set, so it means S will be bounded above. Maximum is equal to supremum. This is very true because if the maximum exists, then the maximum is same as the supremum. The greatest element in S is the least upper bound, and for that case, it means the maximum of S is an upper bound. Because when you look at this set 0, 1, if this is our maximum, this qualifies still to be the supremum. Minimum also exists. This is not necessarily true. Having a maximum does not necessarily mean the minimum must be there. S is empty. This is not necessarily true. So basically, it means B will be the answer. So this will mark the end of our objective questions we have so far discussed in this part 2. We have discussed about 43 objective questions, and this brings us to the total of about 73 MCQ questions and answers. So basically, if you find this video helpful, don't forget to subscribe, don't forget to like, and don't forget to share this video to your friends. Make sure you don't miss any part of this video, and please make sure you put in the comment sections, how many objectives you got right and what were the most challenging parts. So see you in our next video that will be about revision questions. So I will be able to upload more revision questions about real analysis. Make sure you subscribe, like, and share this video. So we meet in our next session.